To simulate how an atom ionizes when struck by an attosecond laser pulse, we have to solve the time-dependent Schrödinger equation. The immediate physical challenge is that the ejected electron doesn't stay localized. Its wave function propagates outward toward infinity. Standard numerical techniques, like finite difference methods or B-spline models, rely on a spatial grid. Because computers cannot calculate infinite space, physicists must draw a hard boundary at a specific physical radius, r. When the propagating wave hits that artificial wall, it bounces back, contaminating the simulation with unphysical interference. To manage this, researchers typically rely on two workarounds: complex scaling or introducing a complex absorbing potential, often called a cap, at the edge of the grid. A cap acts like a mathematical sponge. It arbitrarily dampens the amplitude of the wave to hide the reflections. But this absorption requires no knowledge of the actual asymptotic structure of the outgoing wave function. It suppresses the error, but discards the true physical state of the electron at large distances. For long interaction times or strong electromagnetic fields, the wave packet spreads rapidly. Constantly expanding the spatial grid to contain it becomes computationally prohibitive, and artificially dampening the wave loses critical data. The alternative proposed in this research bypasses the physical grid entirely. Instead, the authors extend the time-independent J-matrix scattering approach to the time-dependent Schrödinger equation. Rather than mapping the wave function to physical coordinates, the continuous wave is expanded into an abstract square integrable L2 function space. Here, the system is divided into discrete mathematical blocks, indexed by the integer n. The boundary is no longer placed at a physical distance from the nucleus. Instead, the boundary conditions are imposed directly at a specific numerical index, capital N, within the function space. This numerical border can be dynamically programmed to become completely permeable to the outgoing wave. Instead of forcing arbitrary absorption like a cap, this method connects the inner simulation directly to exact, analytically known asymptotic solutions. Moving the boundary from a spatial distance to a functional index eliminates the wall. This mathematical translation provides stable, precise models of ionization in attosecond fields without generating grid reflections. To execute this translation, the time-dependent Schrödinger equation is first projected onto a specific one-electron basis set. The specific mathematical tools used for this expansion are Coulomb-Sturmian functions. Look closely at the scaling parameter, xi. By varying xi, the equations can efficiently sample different radial volumes around the atom. But crucially, the index n is not a spatial coordinate. It is a discrete function index. A high n value simply designates a function that spans a larger mathematical volume, not a physical radius. Projecting the Hamiltonian operator onto this specific basis yields an incredibly useful structure, a tridiagonal matrix for the radial components. By using the Sturmian basis, the infinite continuous physical problem is discretized into a sparse system of first-order differential equations a computer can rapidly process. With the equation discretized, the L2 function space is explicitly divided into two domains at the boundary index n. Everything to the left, where n is less than n, is the inner zone, representing the region where the laser field actively interacts with the atom. Everything at or beyond the boundary n is the outer zone. Out here, the model assumes net photon absorption drops to zero, allowing us to drop the laser interaction entirely. The time evolution in this outer zone is governed strictly by the field-free Hamiltonian, h0. Because this region isolates the electron from the laser, the asymptotic solutions to h0 are already known analytically. They behave purely as outgoing Coulomb waves, which expand precisely into Pollaczek functions. The simulation now faces its central mechanical challenge. How do we pass the wave from the numerically calculated inner zone into the analytically defined outer zone without creating a reflection at index n? The solution relies on evaluating the complex expansion coefficients, specifically the ratio of the coefficients right at the border, a sub n-2 and a sub n-1. The simulation evaluates this quotient continuously, executing it during every single time step of the Runge-Kutta integration loop. Furthermore, this ratio is calculated independently for every single partial wave in the system. The coefficients are fed into a Newton root finding algorithm to solve equation 13 for a complex wave vector variable, k. The real part of this calculated k value dictates the direction of the wave's propagation at the boundary. If the real part of k drops below 0, it indicates that the impinging wave is scattering backward. The math is attempting to generate a physical reflection. To prevent this, the algorithm steps in. When a negative real value is detected, it is overridden, forcing the real part of k precisely to 0. This corrected k value is plugged into equation 14 to calculate the boundary coefficient a sub n, feeding back into the simulation. By dynamically adjusting the wave vector k for every partial wave at every fractional time step, the algorithm guarantees the L2 boundary remains entirely permeable, absorbing the outgoing wave packet perfectly. With the boundary logic established, the model must be validated against theoretical limits in the non-perturbative, strong field regime. To test this, the simulation bombards a ground-state hydrogen atom with an intense, ultra-short half-cycle pulse. This graph plots the resulting ionization spectrum. Notice how the energy distribution changes as the electric field amplitude, labeled E0, scales from 0.1 up to 2.0. Right as the external field amplitude hits 1.0, matching the internal atomic field strength, a distinct, pronounced ionization peak forms. Those red dots are not from the L2 simulation. They are analytical predictions derived from the short-time first Magnus approximation. The L2 curves align beautifully with the exact analytical points. The functional boundary successfully models severe ionization dynamics under extreme field strengths without producing any spatial grid artifacts. The final proof of concept examines coherent dynamics induced by two successive, precisely delayed attosecond pulses. Each pulse frees an independent electron wave packet. Because the pulses are timed so closely together, the first packet is still propagating outward when the second is released, causing them to overlap in energy and create an interference pattern. This chart visualizes that resulting interference spectrum across two different field amplitudes. The dashed vertical lines denote specific energy levels. The distance between each line maps precisely to the time delay programmed between the two laser pulses. These mathematically exact gaps are derived from a simple, unperturbed plane wave approximation shown in equation 34. Because the simulation aligns tightly with this plane wave math, it confirms that under strong electromagnetic fields, the Coulomb pull of the nucleus becomes secondary. The complex attosecond interference pattern can be accurately deconstructed as independent, freely propagating plane waves simply overlapping their energies. By abandoning physical coordinates and anchoring the boundary within an L2 function space, physicists no longer have to endlessly expand spatial grids or arbitrarily erase data. They gain a mathematically rigorous, dynamically stable engine capable of resolving the extreme dynamics of attosecond quantum mechanics.